Okay, hello everyone. Welcome back to yet another event. We had our opening ceremony from 1 to 2 p.m. earlier today. Great to see some of you back here. I can also see some people are still trickling in, but we're going to get started now. So this workshop is going to be a coding-oriented workshop. Basically, informing you, teaching you about coding fundamentals in preparation for actually working on your projects. Now, keep in mind, this workshop isn't the only form of support you'll get. You'll also be you also have access to our drop-in sessions from our mentors via Zoom or Discord. And you can also ask any question via Discord anytime or email, and we'll promptly respond to it. So just keep that in mind, that there are many other systems of support for you. So with that said, this workshop structure essentially going to be 50-minute discussion of coding fundamentals, things like that. And then 10 minutes at the end will be allocated to a Q&A session where you can ask Jacob Taylor, the host of this workshop, any questions. He's doing some pretty interesting research, as you will find out shortly. So with that, I think I'll pass it on to Jacob. So give a very warm welcome to Jacob, and he'll be introducing himself and continuing on with this workshop.
Awesome. Thank you so much, guys. I'll go ahead and share my screen. Awesome. So I'm gonna trust that you guys can all see this. So thank you guys so much for having me. Thank you, Science Rendezvous, and thank you guys all for coming. So I'm going to start off with a little bit about what we're going to talk about today. So I'm going to start by introducing who I am, what I do, how do I use computers in my research. We're going to be talking about what is computer programming in general. Why should you care about computer programming? How can you start to write your first computer program? We're going to do a little bit about different basic programming concepts and how to start applying them. And ultimately, I want you to know what is the best way for you as a beginner to become a better programmer. And I want to lay out a framework that you can follow to get to becoming a better programmer. So I'm going to start with a little introduction about myself. So this is a photo of me. I am a third-year PhD candidate at the University of Toronto. What that means is essentially I've been in school for a very long time, and I have a lot longer to go. I do research in a field that's called astronomical instrumentation. So what astronomical instrumentation is I work on the instruments for large telescopes. And there's a lot of computer programming and engineering that goes into that. So I work for these guys, and I have to give them a shout out. I work for the Dunlap Institute of Astronomy and Astrophysics at the University of Toronto. And I also work at the University of Arizona, as you guys are going to see shortly. So I grew up in Ottawa, Ontario. So many of you probably know where that is. And I currently live in Toronto, where I moved once I went to university when I was 18. And I still live there now. But currently, I'm speaking to you guys from Tucson, Arizona, which is a city in southern Arizona, really close to the Mexican border with the United States. And I'm here doing research because the actual telescope that I work for is located near Tucson. In the mountains. So what exactly do I research? So this is the telescope that I work for. It's a large telescope. The big mirror you see here is about 6.5 meters wide. So it's incredibly large. And I work on, you can sort of see it in the foreground here, this little tiny mirror that's in front of the telescope. It's about 1 meter wide. And this is what it actually looks like. So this is a very fancy mirror that has a bunch of magnets on the back of it and a bunch of computers that essentially allow it to change shape. So it's a mirror that is very bendy and can change shape. And the whole reason that we do this is because when telescopes from Earth look at stars and planets in space, the atmosphere, the air around the Earth, distorts the image. And this is what causes stars to twinkle. And for astronomers, this is a really, really tough problem to solve. It basically makes all of our images look very blurry. So on the right, you can see you can see a picture of Saturn and Uranus taken without the ability to correct for the atmosphere. And on the right, you can see what happens when you correct for the atmosphere. So I work on the computer systems that essentially accomplish this correction. So that's a little bit about what I do. I tried to give a little bit of an introduction, but it can be pretty complicated. So with that little bit about myself over, I want to sort of talk about what is computer programming and coding? Like, what does it mean when we say computer programming? So programming is a way to communicate with computers and tell them what to do. So let's look at a few examples where computer programming is used. And a lot of these examples you guys are probably familiar with. We have the applications on your cell phone. So things like Instagram and Facebook and Twitter. You have video games like Minecraft. So there's different video games, and all the different video games, basically you have to program in order to make them. You also have a little fancier things like robots and telescopes. There's a bunch of programming that goes into cybersecurity and keeping you safe online, and other things like finances and the stock market. So really, in the modern day, computer programming is everywhere. It's used in almost every field of engineering, science, technology, and we use it every day. So it's an incredibly important skill to learn in this day and age. So this is a map of all things related to a field called computer science. And programming is a small aspect of this greater field of science, which is called computer science. So this right here is where programming lives. And essentially, computer programming is a way to access all of the other aspects of this map. So if you want to do things like robotics, artificial intelligence, machine learning, augmented reality, virtual reality, video games, you want to do things like data science, all these types of things, you basically have to start with programming. And over the long term, when you get really good, you can move into these different aspects of computer science. And so that's why we're talking about computer programming today. And that's why it's such an important aspect of engineering, and it's such an important aspect of modern technology. The problem is programming is very complicated, and it can be it can be really hard to know where you even start with programming. So what I really want to do today is sort of give you some tools and a little bit of understanding to get you started with programming and point you in the direction that's going to allow you to make the most progress quickly. So just like with every skill you learn in life, you have to start small and you have to work your way up. So what I did is I made a little roadmap for how to learn how to code. So this is a diagram that I'm going to fill in here. As we move downwards, we're going to be talking about as you gain more experience with coding. And then left to right, we have the different type of programming language you can learn, an example of that kind of programming language, and what the goal is going to be while you're learning that language. So the first level here is block programming. So block programming is when you don't actually write code using text, you use blocks of code and you assemble them like Lego in order to end up with a program in the result. An example of such a programming language is Scratch, which you may be familiar with already. And if you're not, I'm gonna show you, we're gonna start working with Scratch. And the goal of block programming is to build a foundation for your understanding that you can then take forward with you when you move on to more complicated programming languages. So after that, the next level I recommend is something called interpreted languages. And these are languages like Python or JavaScript. And the goal is to be able to make code that has a high amount of function without learning a lot of the underlying core concepts. So with a language like Python, you can do almost anything you want, and you can do it quickly and comparatively easy relative to other types of programming languages. So that's where you can move after you've built a foundation with block programming. And then lastly, you can move to more complicated languages These are typically compiled languages like C, C++, Java. You may have heard of them before. And if not, basically, the idea with these types of languages is you're going to build an understanding, a deep understanding of how programming works, how computers work, and how to communicate with them at a very high level. So for now, we're going to start with some very introductory lessons. And we're going to be using Scratch to do these lessons since it's the most simplistic. So the first lesson to learn with computer programming on day one is to understand that a computer follows orders. So what does that mean? A program is a set of instructions that a computer will follow. Computers will execute these instructions in the exact order they're presented from top to bottom. So understanding that a program is instructions written from top to bottom that a computer is going to follow exactly in order. A programming language is a language we use to communicate these instructions to the computer. So there are a variety of different programming languages with a variety of different levels of complexity. But the point is that the programming language is how we communicate the instructions to the computer, but the instructions themselves can be very similar between different programming languages. So now that we have an idea of what a program is, we're going to start and create a very basic program. So I'm using this website called Scratch, which is made by MIT, that allows you to do block programming and start very quickly. So if you go to the Scratch website and you click on Create, you'll be brought to a panel that looks kind of like this. So at first, it can be a bit complicated to understand the different sections of the panel, but I'm going to try and go through them slowly. On the left here, you have a variety of menus that have different instructions you can provide. And you can see that each of the instructions is shaped such that it can build together with other instructions like Lego. On the bottom right, you can see you have these little plus buttons, and this is how you add different sprites and different backgrounds, so different characters. So here you can see I have a cat, but if I wanted to add like a dog or other such things, you can use these menus here to add different things to your scene. For today, we're basically going to be sticking with the cat and focusing on understanding the different commands and how to combine them and what they mean. You'll also notice there's a flag here, and this flag is how you run your program. So when you've built your program and you're ready to run it, you can click on the flag up here. So let's start with a very basic example here. So if we make sure we're clicking on the cat, and then we can drag over from the menu on the left these two commands. And so you can see when the flag is clicked, say hello. What that means is now when you click the flag, the cat is going to say hello. And so this is our first program. It's a set of instructions from top to bottom, starting when the flag is clicked, and then the cat will say hello. So these are the building blocks of a program. Here are a couple more examples of slightly more complicated programs that you can do very quickly. When the space key is pressed, move 10 steps, turn 15 degrees, play the meow sound until done. If you were to write this program and then press the space key, the cat would move forward, rotate slightly, and then you would hear the sound meow. This second program that I've written here is actually what's being displayed by this graphic here on the right. When you click on the cat, or when the sprite is clicked, switch to costume cat B, think So what this does is when you click on the cat, it switches from its running position. You can see the legs of the cat move, and that's switching to cat B, and then you can see it thinks So these are some examples of basic programs, and if you can go online to this website, and they'll have many more examples of programs written by other students showing a variety of different types of statements and examples. So after we know what a program is, the next thing to think about is that a computer can remember things. So we're able to tell a computer to remember things so that we can use them later in our program. We call these things variables. Variables can be changed by instructions in our program and used to build more complicated programs. So let's look at an example of a variable and how you would implement it in Scratch. So you can see on this is a screenshot of the panel that has all the different commands on the left. If you go to the variables menu and then you click make a variable, you'll be able to make a variable. In this case, I called my variable age. And remember that a variable is something that can hold a value and remember it and use it later. So what I've done is I've written a program here. When the flag is clicked, we're going to set the variable age to 25. And then the cat is going to say, right now I am, and then our age for 5 seconds. Afterwards, we're going to change the value of age by 1. And then the cat's going to say, next year I will be age. So this is a very simple example of a variable. And you can see that in the variable menu, you can take these different commands and you can drag them into your program and use them accordingly. So I want you to think about what's going to happen when we run this program and what the cat's going to do. And I'll wait about 5 seconds and then I'll show you the answer. So here's what happens. First, we press the flag and our cat says, right now I am 25. After 5 seconds, the cat will say, next year I will be 26. So that's the answer to what happens when we run this program. So variables can store information. You can change the variable, and then you can ask the computer for the new value. And you can use it to essentially write programs like this, where you can say, right now I'm 25, next year I'll be 26. Now, where variables get really interesting is that we can use variables to change the way a program works. So sometimes we want our programs to do different things depending on the value of our variables. For example, if you're programming a video game, you'd want to change how difficult a boss was depending on the player's chosen difficulty. So for instance, if the player says they want to play on easy mode, you would like to change the way the boss works to make the boss easier for the player. This is an example of when you would want to change the outcome of a program depending on the result of a variable. So in order to do this, we use statements called conditional statements. So here are 2 different menus you'll see in the Scratch program. On the left, you'll see operators, which are in green. And on the right, you'll see what are called control statements. So the ones I've outlined here in red, these are what we call conditional statements. And what they do is they typically compare 2 different things. For instance, this one, the one with the greater than sign, compares 2 values, and it says which value is higher. You can then use these conditional statements, and you can put them inside of these control statements. And once you're inside the control statement, you can change how the program functions. So let's go through an example of this. So here's a program that I've written on the left. When the flag is clicked, we're going to set our difficulty variable to easy. We then go into this control statement. If our difficulty is equal to easy, then we want the cat to say, phew, that was easy. Otherwise, we want it to say, ouch, that was hard. So in this case, what happens, because we have set our difficulty to easy, the cat is going to say, phew, that was easy. And it's not going to say, ouch, that was hard. So we've changed the way our program functions based on the value of our variable. So our variable here is difficulty. We've changed its value to easy, and then we can choose what happens to our program. This is a really powerful concept. So just to reiterate, this is another example. Here we've set the difficulty to hard. And now what's going to happen is difficulty is not going to be easy. And so instead of our cat saying, phew, that was easy, it's going to say, ouch, that was hard. So we've effectively changed the outcome of our program by changing the value of our variable. So the last lesson we're going to talk about is repetition. So one of the most important concepts in programming is repeating the same command many times in a loop. So loops use conditional statements to tell them when to stop the loop. So essentially, if you want to repeat a command several times, you're going to put it inside a loop and then develop a conditional statement to tell it when to stop. So to go through an example to explain that, the program on the left here, when the flag is clicked, we're going to set our variable cat angle to 0. We are going to repeat everything in this control statement, you can see separated by the light orange, until the cat angle is 360. So for instance, we're going to turn 15 degrees, and then we're going to increase the cat angle by 15 and wait. So try and think about, for the next 10 to 20 seconds, try and think about what this program is going to do. We start with our cat angle at 0. Until the cat angle is 360, we're going to be increasing the cat angle. So what's going to happen to our cat over time? All right, I'm going to give you a few more seconds to think about it. And this is what happens. Our cat does a complete rotation. This is a GIF that's repeating over and over again. So essentially, when you click the flag, the cat will do a complete rotation. So hopefully that's clear how this works. Essentially, what we've done here is we've used conditional statements and variables to achieve repeated patterns. Now, you could also complete the same program by repeating these commands over and over again and not inside this loop statement. So you could have many turns, many changes, and many waits. You could write several lines of program. However, what we've seen here is we're able to make it a lot smaller by using conditional statements and variables. So the question really becomes, where is all of this going? So we've looked at a few different concepts in code. We've looked at what a program is, the fact that it goes from top to bottom. We've looked at variables and how computers can essentially store the value of a variable and then use it later. You can then use those variables to change what the code does, and whether you want it to repeat or whether you want it to use an if statement to change the outcome of the program. So what I want to do is I want to look at some code that I've written for my research and essentially identify the concepts we've spoken about. So you're not expected to understand this at all. So this is some code written in C++. What it does is not super important, but it's genuinely code that I've written, and I just took it from my research. And what I've done here is essentially highlighted all the different concepts in the same way that they are highlighted in Scratch. And so what you can see is these 4 concepts, variables, control, and operations, are a majority of this code. And if you can learn the basic fundamentals, you can build up and eventually get to code that does a variety of really interesting things, like control telescopes. So now let's revisit the roadmap that we started with. So far we've talked about block programming and Scratch, and we've seen that it can be a foundation to move on to other things. So how do we move forward? So once you've got a solid foundation in Scratch and other block programming languages, what you can do is move on to interpreted languages like Python or JavaScript and start to look for projects that have a lot more function to them and less foundation. So something I recommend is you can always go into online tutorials. So this is a website, learnpython.org. And at this website, you can essentially do tutorials in Python, Java, HTML, and a variety of other programming languages, really anything you want. And so online tutorials are free, and they are incredibly helpful. Another resource you can use is Microsoft Make. This is a website where you can learn how to build games. You can learn how to program microprocessors, and you can also learn how to create modifications for Minecraft. Another website I recommend is a website called replit.com. This is a website where you can start coding instantly in any language, and you can also share code and code together with your friends simultaneously. So this is essentially, on this website, you can start coding in any language you want, and you can just create a script and run it on someone else's computer, and you can share and invite your friends to code along with you, and it's entirely online and free. So something to think about. Additionally, I find YouTube tutorials very helpful. So for instance, here you can if you just go on YouTube and type build a website using HTML, CSS, JavaScript, and you could follow along on your YouTube tutorials. But ultimately, the best way to learn programming is to find a project that interests you and learn the necessary skills to complete the project. So with programming, it's really important to find something that interests you, and then from there, you can learn the necessary skills once you have a project in mind. Now, I'm realizing I went way too quickly through all that at this point. Maybe what I'll do is to utilize more of the time, go back and start talking more about the various lessons that I was talking about for programming. So maybe we'll think more about these programming lessons here. So starting back with the Scratch interface, I'm going to explain a little bit in more detail how exactly you go into making these programs. So if you start on the left side here, you can see that there's several different categories: motion, looks, sound, events, control, sensing, operators, and variables. So when you start a program on Scratch, the first thing you want to do is select an event. So an event are the yellow things here. So you've seen a couple of them in the examples I've shown. So to start, you can say when the flag is clicked. That's probably the most common event. And that'll initiate the program only when you click on the green flag. After that, you can include a variety of simple statements like say, rotate, move. And these are statements that are going to affect your sprite or your character. You can start with the cat, and then you can move on from there. Using these menus in the bottom right, you can move on to having a variety of different animals, people, objects, backgrounds, and eventually you can create it such that those objects interact with each other. Okay, so let's look at these programs a little bit in more detail and discuss how you actually would create them. So again, you have to start with an event, and in this case, we start with the event when the space key is pressed, and then we have different commands. These are just commands you would drag from the menu: move 10 steps, turn 15 degrees, and you can play a variety of sounds. And you can just look through the menus and find the actions that you want your character to perform. This is a different one that starts with a different event. This event is when the sprite is clicked. That's an event that happens the program only triggers when you actually click on the cat. So you can see in the animation here, when I click the cat, it changes its appearance and then it has a speech bubble. I really would encourage you to go to this website if you're interested, and you can look at a variety of complicated programs that other students have made, and then base your programs off that. So revisiting variables. Variables are probably the most important thing that can allow your program to, your programming to grow in such a way that is going to be add a lot of complexity and a lot of functionality to your program. So in Scratch, the way you actually create a variable is you just go to the variables menu and you make a variable. And then once you have a variable, you can drag it into a variety of the different operators. So you can see here, this program in more detail, it's when you click on the flag, it changes the value of the program age, value of the variable age, and then you can choose what you want the cat to say, and you can change depending on the value of age. So here, I could set age to 24, or I could set it to 22, or whatever your age is. And then the program will run the same, except instead of saying right now you are 25, it'll say right now you are whatever age you put in here. Okay, moving on to operators. So just to cover it again, operators are broken down into two different types. Okay, there's math operators, which are at the top, and this is how you would add two variables together. So in programming, a lot of the time, what you want to do is you want to add two numbers together and see their result. So you can do that in Scratch using operators, and you can do this in a variety of all languages in a very similar way. But the ideas are the same, and they're based off of the idea of operators. And then there's conditional statements, which conditional statements are statements which evaluate to either true or false. So for instance, the first one here says, is the number on the left bigger or smaller than the number on the right? And if it's bigger, then it will do true. And if it's smaller, it will do false. So your conditional statements can evaluate to either true or false, and then they will decide how your program acts. So looking at this example here, we have our variable, which we've set here to easy. And then really what's important here is this conditional statement in green. So our conditional statement is going to check whether our variable difficulty has the same value as easy. And if it does, then it's going to execute this command here. And so because we've set difficulty to easy, we can see that only what's inside of the first section of the control statement is going to execute. And now if we change the value of difficulty and we change it from easy to hard, we get the different outcome. So we've changed the outcome of our program only by changing the value of a variable. And that's what's really important. And that's the concept that generalizes to incredibly complex programs. And I'll go through the repetition one more time, and then maybe we can move into the Q&A after that. So when you're talking about repetition, it's very similar to the conditional statement we were talking about just before. We are essentially using our variable, in this case, cat angle, which is the angle that the cat is going to be rotated at. And we're going to repeat until a condition is met. And our condition here is that our cat angle is 360. So right now our cat angle is 0. And this statement right here, turn 15 degrees, change cat angle by 15, and wait 0.1 seconds. These commands will execute one after the other. You can think of them as being joined. You're taking these statements and putting them one after the other several times until, that's what the until means, this condition is satisfied. So this condition is only satisfied after we've turned 15 degrees 20 times or so. And the result is that because we're waiting between each turn, we observe the cat doing a circular rotation. We're changing the cat angle by 15 over and over and over again. Okay. So hopefully I was able to explain to you a little bit about the basics of programming and how you can take those basics, control statements, variables, and operations from something like block programming, and you can extend it into new languages like interpreted languages, compiled languages, and more complicated programming languages until you're able to have enough expertise that you can move into a variety of interesting fields like making video games, computer vision, machine learning, astronomy, physics, all these fields where this is really the skill, and these are the concepts that are at the heart of the entire field. So with that, I think I'm going to move into the Q&A, and hopefully I can answer some questions for you guys.
Okay, great. Thank you so much, Jacob, for that presentation. So now we're going to open the floor for some questions related to this workshop, what was discussed in the workshop, or even about the research that Jacob does. You can just type the questions in the Q&A chat. And if there are no questions coming in, I will ask some questions for Jacob. Oh.
Actually, I can take some of these questions.
Yeah,
Jacob, a couple of students were kind of, I guess you can say they're very ambitious. They're asking, they want to kind of tie in together software going to hardware, and they're wondering if there are any programs available where they can essentially create like a virtual simulation of a robot that then takes code that they put in the software to control it or make it perform a function, all happening within like a virtual simulation on the computer. Is that something that's available?
That's a good question. I'm sad to say I probably don't know the answer to that. Although I would say I know there are softwares where you can design your own hardware like Tinkercad, but I'm not super familiar with the programming infrastructure in them.
Yeah, I would say the same thing. With my experience, I'm not familiar, but one good recommendation I have for everybody is what we used last year was sort of the same thing. It wasn't a moving robot, but it was a tiny computer called a microbit. You can also go to Microsoft Make Code and access the microbit software development program. And you can directly then control a microbit using block code to make it do really interesting things. And what's even cooler is that the top 5 teams of this competition will be receiving a microbit themselves. So if you want to make a project revolved around them, that means you'll be able to test it if you were able to win the microbit. So give that a try. Okay, thank you.
Yeah, I think another resource also would be the Vex code. It's basically like a block coding interface, and you essentially control this virtual. I don't think it has to be a car, but it's essentially like a virtual like robot car using block code. So that's also something else to keep in mind. It's also in the information package. We did provide a few resources underneath the builder role in the information package, like Vex code, Tinkercad, Make code. We did provide some of those as example applications that you could use. So also make sure that you check that out in the information package.
Okay. So another question, Jacob, is that a lot of the students here seem to be very enthusiastic about learning new other coding languages. A lot of them seem to be, or some of them seem to be familiar with block code. They want to take the next step. with that in mind, do you have any recommendations or I guess words of guidance for students that are aspiring computer programmers?
Yeah, once you have a good foundation, my recommendation is either Python or JavaScript. Most of the students that I've worked with, they start using Python, and then really they start working on command line games. So these are games using a really good website to sort of use to actually write the code would be Replit. This is a website where essentially you can you can just start writing a Python program. You don't have to download, you don't have to install anything, and you can run it, and you can create command line games. So things like tic-tac-toe, blackjack, and you can get more complicated. And the reason behind these games is that actually they have quite complicated algorithms that are not as simple as the you might think. And once you're really testing your abilities to write complicated code, and I find that like simple games like that, I'd recommend tic-tac-toe is always a really good one to start with. If you're able to implement a game like that, you're really improving your skills. Now, another resource that I use very often for people who are really interested in mathematics is this website called projecteuler.com. And it is a website that has it's a large archive of programming problems that are based around math, and they start from very simple all the way up to incredibly complicated. And you can sort them by difficulty, and they're just problems that require a computer to solve. And so these are for any student who's really interested in math and wants to use programming to test their programming skills using math. I would recommend a combination of Replit, so that you have an easy way to just write code instantly, and Project Euler to actually get the coding questions. And because the questions go from very easy to very difficult, you can actually see where you're at and tackle problems that require coding and algorithms that you're not familiar with. So hopefully that was a little bit helpful.
Yeah, absolutely. Thank you so much. And yeah, it does kind of it is an interesting journey, just because depending on what programming language you use, it will make learning other ones a little bit easier. So I highly recommend, because a lot of students are asking, if I learn one, can I learn the other easier? And yeah, it really does depend. Would you say, Jacob, that learning, starting to learn an object-based programming language will help? Like, let's say if you start with Python, learn something like C# a little bit easier and more straightforward.
Yeah, if you go with Python for quite a long time, you can learn object-oriented programming. I find that if you start with something like Java, which is very object-oriented based, it's harder to get started, but once you learn it, there's a lot of benefits to it. Something like C# is very object-oriented, and learning right off the bat, being confronted with a programming language that requires a lot of knowledge right when you're starting, it can be quite difficult. And so you want to use a language that doesn't have all these restrictions in order to learn things like loops and control statements and all those other things. And really starting there, and then once you have all those things down and you're able to write in Python fairly easily, then you can work on object-oriented languages. Although you can always skip, depending. I would say put your interest first. If you're interested in something that requires C# like Unity, your interest should always guide what you are learning. But if you're looking for the simplest path, where you're and maybe the most efficient path, I think typically learning either JavaScript or Python first can be very useful.
Yeah, that's fantastic. I 100% do agree with that, because I had to recently teach myself how to use C#, and looking at it now, the logic behind it, I think, would have been more straightforward had it started with something like Java and Python, for sure. So, Jacob, it's very clear a lot of the students were very interested in your work as a PhD student. And I think a lot of them might be wondering, what was your journey to get from point A to point B? I guess like when you were in their shoes to where you are now.
That's a good question. I first started programming in grade 10 when there was a computer science class that was offered at my high school. I would recommend for those who are starting high school or going to be in high school in a few years that you look into the computer science program that's offered. To my knowledge, it's not offered at every school. And at the time, I didn't realize that. I didn't realize that I was very fortunate. I went to a school that there was one computer science teacher, and she sort of built the program at the school, and it wasn't offered at other schools in my area. Although maybe today it's offered at more schools. But the point is that really I started in grade 10, and through high school, I started by learning C++. And I actually did some competitions in high school where I was competing with other youth. We were sort of a program contest. And then by the time I got to university, what I realized is that by doing programming in high school, I actually had set myself up for incredibly well to succeed in physics, which is what I didn't fully realize that when I was in high school. But when I got to university, all of a sudden we were programming in physics class, and I already knew how to do it all. I knew all my loops, I knew my if statements, I knew that. I even knew object-oriented programming. And it was really coding was really the skill that allowed me to succeed in physics. And I think there are many fields that students don't realize when they're young, that when you get older, there are many fields, including medicine, biology, psychology, social sciences. These are fields where actually people who know how to program in those fields can succeed because it's a very rare skill for someone in that position. And so my journey was, I was really into programming in high school. I continued to be into programming into university, and I got interested in the software side of astronomy, and I started doing research in radio astronomy, working on a supercomputer for Canada's largest radio telescope. And I was doing research in the summer for a few years doing that. And that's how I got interested in it. And that's still today what like programming is really the aspect of the research that I enjoy the most.
Yeah, that's amazing. And in terms of, it's incredible that you're working on something that's working in space, and you're essentially controlling it from all the way down here. Can you provide some type of insight? I know some stuff might be private and you can't really share because it is your research, but maybe what kind of aspect of the are you controlling with the code?
So I'll give a little more context. So this is the telescope, and you can see there's a big mirror here. Okay, 6.5 meters wide, which is very large, and it's a big piece of glass, and it reflects the light. The light comes in from space, and it bounces off of this mirror, and then it bounces onto this smaller mirror that's in front of it. You can see it's sort of suspended in front, and this mirror here is the mirror that can bend. It can change shape, and it can change shape to incredibly high precision, like nanometer precision. So that's a billionth of a meter precision that the shape of this mirror is able to change. And what this is able to do, if you look at this diagram really explains what is happening. The light comes in from space, from a star, and then it gets all wiggly as it goes through the atmosphere. And this is what we see as twinkling, or atmospheric turbulence. And you can actually see this with your eye. If you look at a star, you can see that it flickers. Now, a telescope is essentially a very, very powerful eye. And so the twinkling that we see with our eye that's actually relatively minor for a telescope is incredibly, incredibly important. What it means is that any telescope that is bigger than about a few inches, it is completely dominated by the turbulence of the atmosphere. And so therefore, all the images we get when we look at planets and when we look at stars are blurry. And there's no way of making them sharper. No matter how good your telescope is, no matter how big it is, no matter how much technology you use, the only way to make it sharper is to correct for the wiggles in the atmosphere. So the way to do that is with a very complicated control system and a mirror that can change shape. So this is the mirror that's able to change shape, and on the back of it are several hundred magnets, and each magnet is attached to a coil of wire, and we can change the electricity to change the shape. Essentially, it's quite complicated, but the point is that you can use electricity to change the shape of a piece of glass. It's a very thin, flexible piece of glass, like you can see on the left. And by changing the shape of the mirror to match the wiggles in the atmosphere, the result is that once it bounces off the mirror, what hits our detector doesn't have this blurring, doesn't have this motion anymore. And so that's what's being shown here on the bottom right. This is with and without the technology of the mirror changing shape. And so this is on the right here is an actual image showing the kinds of improvements you can get by correcting for this atmospheric turbulence. And so the mirror actually not only has to change shape to a billionth of a meter precision, it has to do that 1,000 times a second. So within a millisecond, we have to measure the distortion from the atmosphere and apply a correction for the distortion by changing the shape of a mirror to incredibly high precision. And so you can imagine that the amount of programming that goes into something like this is truly a lot.
Yeah.
And so that's what I work on. I work on the control system here. So you can see the big control box here that pops up. That's where a lot of my work is.
That's you. That's amazing. That's
Yeah.
incredible. Yeah, I think this is really inspirational, kind of showing the kind of avenues that you could take towards a career by learning the important skill that is coding, because it is becoming more relevant every day, as you said. So we are kind of getting close to the time, but I have two main questions for you. The first one is, do you have any advice for our students regarding how they can further refine their programming skills?
Yeah, the main thing is like in all skills, and everyone will tell you this, is that if you would like to refine your skills, you have to practice. Now, the difference between something like, practicing a skill like your French or whatever, something like programming, is that you can really guide it based on whatever you're interested in. So if we go to this picture here, right? Every single thing in this picture is enabled by programming. So if you're interested in graphics, you're interested in math, science, machine learning, computer vision, all of these things, whatever you find interesting, you can work towards that. And the possibilities are truly endless. And that's almost by design for programming. The whole point is that the possibilities are endless. And so it can be overwhelming. And it can be difficult to find something that you are interested in, that you want to do. So what I really recommend is focusing on finding a project or something. Like if you want to make a video game, start there. And so a lot of the websites, for instance, like Microsoft make, they know a lot of students are interested in Minecraft. It's a very popular video game. And so they've made an entire course and series on how to make modifications to Minecraft. And the reason that something like that is successful is because the students who do that are interested in that. So if you're interested in a robot, or you're interested in in something like that, if you start there and decide what you want to do, there's almost always a way to do it. And asking for guidance when you have a clear idea of what you want to do can be the long term the way to make the most progress. For me, that was really at the start. It was these competitions I was doing through school. We were building small games and other things, and I just really wanted to win, and so that really what drove me to learn things that I wouldn't learn in school until second or third year university. That I just decided I really cared about it in high school because I was very competitive. So that's having a clear goal is my main advice.
No, absolutely, and that's essentially what we're trying to encapsulate with this hackathon competition is to provide students with the opportunity to enter a competition and have enough freedom to create something that they're passionate about, and obviously frame it within the goal of the competition, which in this case is environmental sustainability. So with that said, in terms of the competition, our students really have about 2 weeks to kind of come up with a project. And a lot of them are interested in using block code or just programming something really cool, whether that be a game or an app. Do you have any recommendations to them in terms of how to plan their strategy to create a software? And maybe what are some strategies to communicate with other team members to make collaboration more efficient?
So when it comes to collaboration in code, it can be very difficult because your code is often, you'll write your code on your own computer and then you won't be able to, you'll be sending it back and forth. I would really recommend for a project like this, using a service like a website that there are websites that allow you to code simultaneously with your group members. The one that I use is replit.com, and this you can share. You can create a file in whatever language you like, and you can share it so that it runs. You can share it with your friends. It's essentially like Google Drive. If you guys have used Google Drive for like documents, you can work on them simultaneously. And if you're not using something like if you're using Unity or something like that, it can be more difficult because you're using a program where all your code is kept. But for building something in Python or just sharing code back and forth so that someone can make modifications quickly for a competition like this, I would recommend a website like this if you can use it. And if you want to, I think the question was. How can you collaborate? So that's how I would collaborate. And then if you would like to build something, really it's just about communication. So just keeping your fellow group members updated on what you're doing and asking for help and insight whenever you think you need it.
That's fantastic. And I guess just the last thing is framing a goal. Would you recommend them to maybe scale down if they have really big ambitions in order to make the project feasible for the amount of time?
Yeah, the scale is the hardest thing for these kinds of projects. We have a saying is don't reinvent the wheel. Don't try and if you have a big goal in mind, that's really good. You want to find a small thing you can do towards a larger goal. So whenever I would advise students on presenting for these kinds of competitions, you want to present your overall goal, but you're only going to be able to accomplish a small part of that in the amount of time. So don't get too concerned about accomplishing your whole goal. Really, we're looking for, maybe a prototype or something like a smaller scale realization of a larger goal. And that's really what I think the best kind of projects for something like this is large scale ideas with small scale realizations that are working towards a greater idea.
100%. That's fantastic. So I did say this would come to the last question, but we actually have some students that are very interested about your schematic. So I guess before you go, can you return to your schematic about light and going back to the telescope? One of them are some students are interested in they're asking about how are you able to manipulate such a large object in such tight tolerances by using code. So I get going from software to hardware again.
Okay. So really, I'm going to start using some, maybe because these questions are a bit more complicated, I'm going to have to start using a bit more like jargon. But what these things you see on the back of the mirror, these are called actuators. And essentially they are very, very special actuators. Each one of these actuators, and you can see it in this image on the right, you see all these little boards that are sticking out, these little, those are actually the heat tubes that cool the actuator down. But you can see that each one of these magnets corresponds to one of these yellow sticks. And what those are is each actuator is what is responsible for moving a particular part of the mirror's surface. And they do it by changing an electrical current. And if you study physics, you might know that electrical currents produce magnetic fields. And so magnets can be moved with electrical current. And each actuator, which is what's moving the mirror, has its own brain. It has its own circuit board that basically allows it to determine where it's at and make sure that it's in the right position. And it's able to do that incredibly quickly. If it seems impossible, I myself am very shocked by how amazing technology is these days. But basically, smart people just spend a lot of time figuring this out. The first one of these mirrors was invented in 2002. It was not invented in 2002, it was invented in the 90s, but it was used in 2002. So actually this kind of technology has been around for quite a long time at this point. And all we're doing with the new mirrors is just making it way, way, way better. Essentially you can move things very precisely with electricity, and electricity is, computers can choose to manipulate electricity using controllers and other types of processors. And so in short, we have very fine control using a variety of smart actuators that are hooked up to a big controller that can change the voltage that's applied to each actuator with incredibly high cadence and precision. So I don't know if that is a helpful answer, but that's the real answer.
Yo, that's fantastic. And I guess the last comment that we have here is just in that same vein, the way that you're measuring how the twinkle phenomenon is moving and how to adjust for that, those measurements, how are you tracking that?
That's an amazing question. We use something called a wavefront sensor, which is, you can see here, WFS. I wish if I had known we were talking about wavefront sensors, I would have had a whole slide on them. My thesis is writing the code for our wavefront sensing camera. Essentially, the way you do it is you build a very specialized camera and a very specialized type of optic. It's actually, we use a pyramid of glass. So imagine like the pyramids of Giza, like the pyramids in Egypt, except it's about an inch wide or a few centimeters wide, and it looks like a diamond. It's like very shiny, and we basically put the light, we focus it onto the tip of the pyramid to like micrometer precision. And then when it goes through the prism, it ends up on a camera that is like $1 million camera that we got from the Air Force for free. Which sounds crazy, but it's true. And it's an incredibly sensitive camera, so sensitive that any stray light completely it completely saturates the detector. And so a combination of very precise optics and a very sensitive camera, we're able to take measurements of the atmosphere by looking at the picture of the star over the course of 1 millisecond. And we can then use that information to extract the precise shape of the wiggles and then cancel out the shape on the mirror. And this is actually an example of a textbook control loop that is present in a variety of systems. This one is just an incredibly complicated version of that. So the answer is it's very difficult, and there was many years of study to try and figure out how to detect these wiggles. And we're now able to do it. And you need a really fancy piece of glass and a very fancy camera in order to do it.
I think that's incredible. I mean, they're working with the armed forces to provide you with that type of equipment. That's amazing.
Yeah, they were going to recycle it, but
they were going to recycle it. Wow.
Yeah, they didn't get it anymore.
Okay, we were just talking about repurposing technology in our opening ceremony. So here's another great example of repurposing technology that's going to be recycled to something amazing as to being able to detect stars by such a distance. That's amazing. So I think we've reached the end of our workshop, and I think to close it off, I am going to hand it over to Blake.
Right. Thank you all for coming. Thank you, Jacob, for being a guest for this workshop. Great presentation, great Q&A session as well. So for all the attendees here, note that we do have a workshop tomorrow on science and design. It's going to be from 1 to 2 p.m. And then we have a graphic design workshop as well on April 30th, which is going to be from 2 to 3 p.m. And those are all Eastern Standard Time. Also keep in mind that if you have any questions that weren't answered here, you have maybe other questions that come up after this webinar is finished, you can ask us on Discord or on email. We'll be very responsive with that. And also remember that we do have drop-in sessions as well, starting on April 27th. So that's something to look out for as well. Yeah, so just continue, I guess, forming teams, maybe digesting the workshop that we had today, as well as the one tomorrow. And yeah, just continue to ask us questions on the Discord or email. And we'll see you at our next event, if you decide to come tomorrow. Okay, take care, everyone. Bye-bye.
Bye, guys. Thank you so much.
Take care, Jacob.
Thank you, Jacob.